Hello. Hello. Salutations. Greetings. Hey, hey. Hey, yeah. Morning. Oi, oi, oi. Waiting on maybe one or two more viewers. I'll wait one more minute. I saw the movie Tenet this weekend. Crazy. Good movie. Check it out. Apparently, movie theaters in Orange County are opening up, so that's where I went. I went to Brea and saw it. Um, they just have like every party has to have a gap of one or two or a couple seats between them. I actually did not find Tenet to be that confusing at all. I thought that it made more sense than uh, it made more sense than some other Christopher Nolan films. Like it made more sense than um, what is it? Inception. Inception didn't make a ton of sense to me. And then Christopher Nolan has another movie, like one of his first movies was called Memento. Has anyone seen Memento? And Memento is also a pretty confusing movie. Yeah, I agree. Interstellar is the best. Interstellar makes a lot of sense. Memento is about a guy who only has short term memory. He doesn't have any long term memory. So he basically just periodically forgets what um, what just happened. So that's a pretty interesting movie. Okay. All right. I think I have enough people to get started. Um, you're talking about Memento. Yeah, I think Memento ended up. It was pretty clear. Yeah, it's just difficult to watch. I would say with Tenet, I would probably want to see it again just to catch the little details. But It's a pretty cool movie. And it overall made sense the first time watching it, which I was surprised. Okay, so what are we going to learn about today, class? We are going to learn about inclined planes. All right, inclined planes. So we're going to start off with just the basic treatment of inclined planes, and then we'll go to more complex stuff with inclined planes. So the basic description of an inclined plane is you have some kind of a slope of angle theta, okay? And you have a box, and the box is sliding. So the box could be sliding up the incline, or it could be sliding down the incline. That's going to determine the direction of the frictional force. Let's suppose the block is sliding down the incline. Okay? So in that case, that the box is sliding down the incline, then friction is going to point up the incline. So if I were to draw a free body diagram of the forces that are acting on the block, we would have the weight force, mg. We would have friction, which goes parallel to the incline but in the direction of up the incline. So it's going to point in this direction. There's friction. It's going to be kinetic friction because the block is sliding. And then we have the normal force, which points perpendicular to the incline, F sub n. Okay? So now what I'm going to do is I'm actually going to rotate this whole picture by theta. What would happen if, let's say this angle right here is 60 degrees. What's going to happen if I rotate my paper by 60 degrees? What happened to the incline? It became flat, right? And notice how if I look at my piece of paper like this, notice how the normal force points in the y direction and the frictional force points in the x direction. Okay? And then the weight force is now angled. Okay? So when we rotate the picture, by the way, how much was the weight force angled? Because I rotated the piece of paper by an angle theta, the weight force got rotated by an angle theta. So that is theta. You see what I'm saying? So I'm just going to take this whole picture and just rotate it by theta degrees so that F sub k is now this way. The normal force is now straight up and down. And the weight force is now at an angle. And we rotated the piece of paper by theta degrees, so this angle right here is theta. Okay? And I'm going to call this direction the positive direction. Okay? And so now what I'm going to do is I'm going to take my diagonal force and I'm going to break it up into components. So this right here is mg cosine of theta, and this right here is mg sine of theta. Okay? So, so doing this, now my free body diagram looks as follows. I've got normal force, I've got kinetic friction, Okay. I've got mg cosine theta going down. And I've got mg sine of theta going to the left, which is the positive direction in this case. Okay? So let's pick some concrete numbers here just to have this make sense. Let's say that the angle of the incline is 60 degrees. Okay? Let's say the mass of the box is 2 kilograms. Okay? So if I plug in the numbers for mg cosine theta and mg sine theta, what I get is this would be 2 times 10 times cosine of 60. So that's just going to be 10. 10 newtons. And then for this one, I have 2 times 10 times sine of 60, which is 17.3 newtons. Okay, so that's where I'm at. Now, here's the big question, or here's the big realization, I guess, in this problem. The normal force and this force have to be equal in size. Because what would happen if these two forces were not equal? That would represent a situation where the, remember, because we've rotated this picture, okay, the block is now moving horizontally because we rotated the picture. So if the normal force was bigger than 10 newtons, the block would be jumping off the incline. If the normal force was less than 10 newtons, the block would be getting crushed into the incline. Okay? So the only sensible option where the block is actually sliding along the incline, parallel to the incline, would be for these two to be equal. So in this case, the normal force would be 10 newtons. Okay? Now, if the normal force is 10 newtons, let's suppose, for example, that the coefficient of kinetic friction is 0.3. All right? That's going to allow us to calculate the coefficient of, or the kinetic friction force. The formula for kinetic friction is mu sub k times normal. I'm doing the right lesson, aren't I? Let me just double check my calendar really fast. We did types of forces last time. Yeah. Okay, I'm good. I just panicked for a second. I was like, what if you guys have no clue what I'm talking about? Okay, so the coefficient of kinetic friction is 0.3. The normal force is 10 newtons. So I have the kinetic friction force is going to be 3 newtons. Okay, so this is 3 newtons. So now what we want to do is we want to do Newton's second law. So we have net force equals ma. And which direction is the motion along? Well, the direction is horizontally in this picture, but it's diagonally in this picture. See, in this picture, we rotated it so that the block is moving horizontally. Okay? So this is the net force in the x direction, and this is the x component of the acceleration because we rotated the picture. All right? So the net force in the x direction is 17.3 to the left and 3 to the right. So the net force is going to be 14.3 newtons. The mass is 2 kilograms. Oops, why did I write 3? 2a. All right. And So we would divide that, we get 7.2 meters per second squared is the acceleration of the block down the incline. Okay? So, and then using that, we could calculate things such as how fast is the block going to be able to go up the incline, things of that nature. Okay? So this is the standard inclined planes that I go over in AP Physics 1, and I think I might not even go over this at all in IB Physics SL, but yeah, so this is either review or it's an introduction to the inclined plane. Now let's make it a little bit more challenging by adding additional forces. Okay. So let's do another example. What if I have an incline and the angle of the incline is 20 degrees? Okay. The angle of the incline is 20 degrees, and we've got a block. And let's make it a 3 kilogram block. All right. The coefficient of kinetic friction is, let's make it pretty small. Let's make it 0.2. And let's suppose that we apply a horizontal force of size 10 newtons. Okay? So it's a horizontal force. It's not a force that's going up the incline. All right? It's a horizontal force. So let's draw a free body diagram for the forces that are acting on this 3 kilogram block. It's got a weight force, which goes downward, and that force would be 30 newtons, m times g. It's got this 10 newton applied force. Technically, I should have drawn this as 1/3 the length of that one, but I didn't. Okay. You've got the normal force, which goes perpendicular to the incline. And then you've got friction. Now, I got a feeling that the 10 newtons, because I got a feeling that 10 newtons is going to be enough to actually push the box up the incline. Okay? So that means that friction is going to point down the incline. All right? Now, if my guess was wrong, we'll reach a contradiction at some point in the problem, so I'm just going to assume that it's going downward. Okay? So now what I'm going to do is I'm going to rotate the whole page by 20 degrees so that the incline is now level. Okay? So I'm going to rotate by 20 degrees. Now, what does that do? If I rotate by 20 degrees, that makes the normal force up and down. It makes kinetic friction go to the left. It rotates the weight force by 20 degrees to the left. It rotated the weight force 20 degrees to the left. And then it rotated the 10 Newton horizontal force 20 degrees down below the horizontal, so that this is 20 degrees. Okay? So I'm going to rotate the whole picture by 20 degrees, and then it looks like this. This is 20 degrees, so 10 newtons. And then we have this is 20 degrees, and that is 30 newtons. Okay? So basically, this is the same problem we did last time, but I've added this 10 Newton force in there. Okay? All right. And I think that the block is going to be moving up the incline, which would be to the right. So I'm going to call that the positive direction. Okay? Now what I'm going to do is I'm going to take these known forces and I'm going to break them up into components. Okay? So 10 sine of 20 is 3.4 newtons. 10 cosine of 20 is 9.4 newtons. 30 sine of 20 is 10.3 newtons. And then 30 cosine of 20 is 21 or 28.2 newtons. Okay, so the reason that I kind of like spaced out and stopped talking for a second is because I realized that my guess was wrong for friction. Okay? Why was my guess wrong? Well, if we look at, so let me just draw this again, just so that we can be more clear. So we have normal force going up. This force right here can be thought of as a 9.4 Newton force going this way and a 3.4 Newton force going down. Okay? This force right here can be thought of as a 28.2 Newton force going down and a 10.3 Newton force going to the a 10.3 Newton force going to the left. Okay? So as we can see, based on this, see how the leftward force is greater than the rightward force? So that means that the box is going to accelerate to the left. Okay? Which means if the box is accelerating to the left, then that means that friction is going to point to the right. So I goofed. Okay? So this should have been the opposite direction. This should have been the opposite direction. But notice how I just made a guess. Okay? And I'm actually going to retroactively reduce my coefficient of friction, I hope you don't mind, to 0.05. So it's really slippery. It's like almost frictionless. Okay. So now what we're going to do is we're going to solve the problem. So what is the net force in the y direction? Well, in this case, because the block isn't jumping off of the incline or getting crushed into the incline, the net force in the y direction is 0. Okay? Now, what are the forces in the y direction? Well, we have the normal force going upward, and we've got 28.2 and 3.4 going downward. Okay, so I have minus 28.2 minus 3.4. All right? And so this is really easy to solve for the normal force. We just add these negative terms to the other side, we get that the normal force is 31.6. I don't know why I did that on a calculator, but I did. Okay, which in turn, so the normal force is 31.6 newtons, which in turn allows us to calculate the friction force. So friction is going to be mu normal. So mu is 0.05. 0.05 times 31.6 equals I'm going to reduce friction again. I messed up because you can get like contradictions in this type of problem, and I keep getting contradictions. So I'm going to make it 0.02. Sorry, you're my guinea pig class. So I'm making it 0.02. And that makes friction. Oh my gosh. Nope. This is embarrassing. 0.01 is friction. There's extremely little friction on this ramp. 0.01. So that means that friction is 0.32 newtons. Okay. Sorry about that. So friction is 0.32 newtons. Okay. So now we're going to do the net force in the x direction. What forces do we have in the x direction? Well, we've got 10.3 newtons to the left. Okay. We've got, so I'm going to make, because it's not moving to the right, I'm going to make leftward the positive direction. 10.3 newtons to the left. I've got 0.32 to the right. And I've got 9.4 to the right. And that has to equal MA. All right, so that equals 3A. So, and that's because the box is accelerating along the x direction, which would be along the incline. Okay, so I can easily take this and solve for the acceleration. 10.3 minus 0.32 minus 9.4 divided by 3 gives us an acceleration of 0.2 meters per second squared. And that is in the direction of down the incline. So basically what we have here, is there's a 10 Newton force that's trying to stop it from going down the incline, but it's not succeeding. Okay? Trying to stop it from going down the incline, but it's not succeeding. All right. So let's just sort of review the steps, okay? Kind of step one when you're solving this problem is draw the free body diagram, okay? Step two is going to be to rotate it. So the incline is in the is horizontal. You don't have to do that step if you can think about it such that, you know, if you can just kind of rotate it in your mind, that's fine. That's what I would tend to do. I wouldn't redraw this free body diagram as this. I'm comfortable just tilting my head. But it might be helpful to some of you to just rotate it. Then what we want to do is break the diagonal forces into components. Break the diagonal forces into components. So that was the step of going from here to here. So we use trigonometry to make this diagonal force a horizontal and a vertical, this diagonal force to be a horizontal and a vertical. Then what we do is we basically solve for the normal force. Okay. Using the fact that the block is not jumping off the incline, so the net force in the y direction equals 0. Okay. Then we compute friction. So here I calculated the normal force, and then you can see I got friction. And then the last step was to calculate the acceleration in the x direction using net force in the x direction equals ma. All right. Let's just talk about this intuitively for a second. If we think about what is this horizontal 10 Newton force doing, the horizontal 10 Newton force is partially pushing into the incline and partially pushing the block up the incline. Okay? Now, the part of that 10 Newton force that pushes the block into the incline, that has the effect of raising the normal force. Okay? If you take something and you push it into the ground, you're increasing the normal force on that object. So this 10 Newton force increases the normal force, which in turn is going to increase the friction beyond what it would be if there was no force. Okay? So yeah, you kind of have an interplay between horizontal direction and vertical direction. All right, so that's my lesson for today. And so we're going to jump over to the Zoom room, and I will answer any questions you have. All right, so you got a little bit of extra time to work on the problems today.